Let's say here I plot a system with a loop gain, and it is a loop gain with a DC value and 3 poles, of which these are the frequencies because I plot only the magnitude characteristic here. So here we have the magnitude characteristic of a 3-pole system in which the 3 poles are real and well separated. Otherwise you have, maybe you just skip one order, it goes immediately from -2 to -3, and then, you know, you cannot make these lines so beautifully as I have done it here. So this is a simplified example, but it tells you exactly how the procedure works. It illustrates the procedure. So this is the DC loop gain. This asymptote we could write as LDC times P divided by omega, because it's a first order roll-off here, according to this line. And we only, let's say here, the effect of the second pole is not yet found, so you can skip all the other terms. So you basically have only a first order system. But this doesn't hold beyond this point, so the asymptote here is the next one. The next coefficient basically determined by the next coefficient of the differential equation. So here we have omega squared and the product of the 2 poles and the DC loop gain. And probably with me you already understand that the last section will be LDC times P1, P2, P3 divided by omega to the power of 3. So these are the equations for the asymptotes, and the real curve, of course, is different, but we want to deal with the asymptotes because that is more simple. Now let's study the servo function, and the servo function is 1 over LDC. It is minus LDC divided by 1 minus LDC, which means that if LDC is very large, this distance goes to 0, but it will be 1 over LDC under this line, below this line. And then here the next, if the loop gain drops below unity, then the servo function just follows the loop gain. I think this may be clear, but maybe it needs some explanation, because we have like servo equals minus L divided by 1 minus L. So if L is very small, it just says minus L divided by 1. So for a very small loop gain, the servo function equals the loop gain, and for a very large loop gain, the servo function equals unity. So now let's study the intersection points. So this I already told you is approximately 1 over LDC. And here, if it was a first order system, if there was no second pole, then the bandwidth would have been of the servo function there, where we have this equation, where this line intersects with this asymptote. That would be the -3 dB the MFM frequency of the servo function. And you see, we can solve this equation. This is like this line equation, and the other line equation is here. We can solve the equation, and you find the first order bandwidth as 1 minus LDC. Indeed, as we predicted, the product of the pole, the only pole we then have, and 1 minus LDC. So if it is a second order system, then we find the intersection point here, this one, this asymptote, and this one, which is this omega 2, and this is this equation. So this line equation equals this purple line, and you can solve this equation, and you can see omega squared. So the second order bandwidth squared is 1 minus LDC times P1, P2. And if it was third order, then we would have had this intersection point, which means that we have the equation of this line equals this line. This is this equation, and we find this one exactly as we found. The bandwidth is then the product of the poles and the loop gain. So the nth order bandwidth to the power of n is the product of the n dominant pole and loop gain. So in this case, you see we have a second order system because the purple line we already sketched is for high frequencies. We have the servo function approximate the loop gain if the loop gain is smaller than unity. So we have this purple line. So we don't have this, we have this. So we might say this is a non-dominant pole and the other two are dominant. So you could say, as a definition of what is a dominant pole, a non-dominant pole anyway, is a pole that is further than the achievable bandwidth. Well, then we can make a procedure for finding it. So let's first draw the whole characteristic now. Let's say we want to have a frequency independent asymptotic gain, and we have this servo function, then we will find this response. This one, the asymptotes, and of course this pole will be there, but it is non-dominant. Here, the gain will drop with respect to the ideal gain. So here is the bandwidth limitation set by the two dominant poles, and the third dominant pole plays a role, but far away. But you can imagine, of course, if it comes close to the achievable bandwidth, that its influence cannot always be ignored. And later on, we will try to find a technique that can help us in telling you what will be the influence and can we do something about it. So dominant poles, P1, P2, non-dominant pole, P3, and a pole is non-dominant if the magnitude of the loop gain at the pole frequency is smaller than unity. That's another definition. You can make many definitions of dominant poles. Now here's the procedure. We first rank the poles of the loop gain in ascending order. So we start with the smallest, then the larger, then the largest. And then we calculate the 3 dB low pass cutoff frequencies for each order. So that's exactly what I did in the picture. So the first order frequency, cutoff frequency, will be 1 minus LDC times P1. The second order will be the square root of 1 minus LDC P1, P2. And the third order will be this one, exactly as predicted. Now we stop this frequency as soon as the cutoff frequency increases, because if it increases, if it gets smaller, let's go back to the figure. Here, we find omega 1. Then we find omega 2, it's smaller. And then we find omega 3, and it's larger, because this is below. Which means as soon as the number goes up, the previous one was the one you were looking for. And you can also say, if P3 is larger than omega 2, you can stop, because that will increase this number. So the order of n is the number for which this cutoff frequency has the smallest value.